Science Help Now here. Topic 6 is work, energy, and power. This section, section 6.2, is a continuation of section 6.1. In section 6.1, we started 5 problems on work from a mostly qualitative perspective. In this video, we're going to complete each of those problems, finishing all of the calculations to determine the work done or not done in each of the examples. Here we go. So how is work defined in physics? Well, work is done in physics when a force affects the displacement of an object. Now, when the force and the displacement are parallel, work is simply the product of the force and the displacement. Since it's a product, you're going to multiply the force times the displacement to calculate the work. Let's look at the equation for work that's based upon this definition. A lot of the time, you will simply see an equation that says work is equal to F times D, the force times the displacement. But do keep in mind that that implies that you already know that the force is parallel to the displacement. In a later video, we will deal with forces at an angle, and we'll have to actually calculate the component of the force that is parallel to the displacement. But we're going to keep the calculations very simple in these early videos on work. So, if work is equal to force times distance, then the unit for work would be the unit for force, which is the Newton, times the unit for displacement, which is the meter. So this is a Newton meter, and you would just say Newton meter. Now please note that it is not Newton per meter. Remember, if you see a division sign, you say the word per. This is not Newton per meter. Don't draw them on top of each other. They have to be next to each other because they're being multiplied. So again, 1 unit for work is the Newton meter. Now remember that force is also equal to mass times acceleration. So let's look for another version of the Newton meter. The unit for mass is the kilogram. The unit for acceleration is meter per second squared. And the unit for displacement is the meter. So what we have here is another way to write the unit for work. We're going to call it the kilogram. There's 2 meters multiplied, so that's meters squared per second squared. All right, so a Newton meter is equal to a kilogram meter squared per second squared. All right, try to say that. Maybe pause the video and say this unit. All right, kilogram meter squared per, remember when you see a division sign, say the word per second squared. Now, both of these are also equal to a special name called the joule, abbreviated capital J. So, all 3 of these units are exactly the same. A Newton meter is a kilogram meter squared per second squared is a joule. All right, in the problems we're doing today, we're just going to write the word, we're going to write capital J for joule. Let's keep it simple. This is the same example number 1 from the previous video. We started this problem in the previous video. We're going to finish it now. So whether you saw this problem once before or you're seeing it for the first time, you'll be able to do it. Here we go. So you are lifting a 2 kilogram textbook half a meter straight up at constant velocity. So basically, your hand is putting an applied force upwards on the book and the book goes straight up at a constant velocity. All right, so here we go. The steps to analyzing a work problem, trying to calculate the work done. All right, so first you draw a free body diagram. All right, so it's the book that we're talking about, so let's draw the book. All right, there's the book. Now, on a free body diagram, you want all of the external forces on the book labeled with the magnitude and the direction. So far, you have the mass of the book, so you need to convert the mass into a force, or the weight of the book. The equation for weight, Fg equals m times g. The mass of the book is 2 kilograms. The acceleration due to gravity for the Earth is 10 meters per second squared. We multiply those two numbers, and the weight of the book is 20 newtons. Now, sometimes if your teacher wants you to put a negative there for the acceleration due to gravity of the Earth, which is down, then you would put a negative for the weight. All right, the weight is also down. So, straight down, we label the weight of the book, Fg, is negative 20 newtons. Now, since the book is moving at a constant velocity, Newton's first law applies, and we know that the net force in the direction that it's moving must be 0. Therefore, we know that the applied force on the book is also 20 newtons. So F applied is therefore positive 20 newtons. All right? Now, the displacement is straight up. So I'm going to label the displacement right here in red. All right? The displacement is 0.5 meters, half a meter straight up. Keep in mind, these arrows are not to scale. I am not drawing the vectors to scale. All right? If this one is 20, then that can't be 0.5 if it's to scale. All right? Now, it would be two different scales anyway. You've got force and displacement, two different scales. So we're only worried about the direction. We're going to label the magnitude manually, and we'll worry about the direction. All right, so here we go. Now we want to look at which forces are parallel to the displacement. And we see that the applied force is parallel. All right, so Fa is up and the displacement is up. All right, so the applied force is doing positive work. All right, and the gravitational force is down. And the displacement is up. All right, Fg is down. The displacement is up. So that means that the gravitational force is doing negative work. All right, now keep in mind that the net force here is 0. All right, if you calculate the net force vertically here, the net force is 0. Positive 20 plus negative 20 is a net force of 0. All right, now let's calculate the work done by the applied force. So work is equal to the force that is parallel times the displacement. All right, the force that is parallel to the displacement times the displacement. Well, the whole force is parallel, so let's not worry too much about that. All right, so the force is positive 20 newtons. The displacement 0.5 meters. So the work done is 10.0 Newton meters, and that would be 10.0 joules. A Newton meter, see Newton times meter, a Newton meter is a joule. So the applied force does 10 joules of positive work. All right, let's look at the gravitational force. All right, again, the calculation, work is equal to the force that is parallel to the displacement times the displacement. Well, the whole force is parallel. All right, so we don't have to worry about that too much. Now, the force here is negative 20 newtons. The displacement is 0.50 0.00 meters. So the work done is negative 10.0 Newton meters, or negative 10.0 joules. All right, so the work done by the applied force was positive 10 joules. The work done by the gravitational force was negative 10 joules. Now, the net force is 0 newtons. All right, so ultimately, the net work is going to be positive 10 plus a negative 10. The net work done is 0 joules. All right, this force did positive 10 joules of work. This force did negative 10 joules of work. Ultimately, the net work done was 0 joules. Okay, very, very, very simple. You're basically just multiplying the force by the displacement. Problem number 2. Always start with a free body diagram. So you're holding the textbook straight up. All right, so here's the textbook. All right, free body diagram. What are the forces on the textbook? All right, the mass of the textbook is 2 kilograms. Mass equals 2.00 kilograms. You want to draw the forces on the book. Mass is not a force. Weight is a force. So we convert the mass to the weight of the book. Well, how about if you just take mass and multiply it by acceleration due to gravity of the Earth, right? To get the weight, Fg, you take the mass and multiply it by acceleration due to gravity. But for the Earth, that's 10. So 2 times 10 is 20. All right, the weight of the book, Fg, is negative 20 newtons. All right, now if you have to show the work, you're going to have to write that all out. Okay, now, we know that the book is being held straight up. So in the vertical dimension, the book is not moving. The book is at rest vertically, which means that the applied force on the book is positive 20 newtons. All right, now, if we're walking to the right, let's look at this one more time. We looked at this in the last video. If there is no friction, when you start moving to the right, the book is going to slide right off your hand to the left. So there must be friction. Now, if the book is trying to slide to the left relative to your hand, all right, the book is trying to slide to the left relative to your hand, then the friction must oppose that motion. The friction must be to the right. So as I'm moving 3 meters to the right, the friction is to the right. So we draw the friction. All right, we do not know how much the friction is. FF. All right, we don't know how much the friction is. And right now in this problem, there's not going to be enough information to calculate the friction. We're just going to look at the friction qualitatively. All right, but here we go. Now, the displacement. All right, after you get your free body diagram done, decide whether or not there is displacement of the object and the magnitude and the direction of that displacement. Well, we've got 3 meters to the right. So the displacement in this case, D, equals 3.00 meters, and that is to the right. All right, so step 1, free body diagram. Step 2, figure out the displacement, label the displacement. Don't put the displacement on the free body diagram. Put it just off to the side. Displacement, velocity, and acceleration, and mass, for the most part, belong just off to the side, not so much on the free body diagram. All right, now, you want to decide if any of these forces are doing work. So you want to look at the orientation. Are the forces parallel to the displacement? So the applied force, FA, the displacement to the right, all right, that's not parallel, all right, that's perpendicular. So the applied force is doing no work when you walk straight across to the right in the room holding the book up. The applied force is not doing work. The gravitational force is down. The displacement is to the right. Right? No part of this force is parallel to that displacement. So the gravitational force is doing no work. Now, the friction is to the right. All right, FF is to the right. The displacement is also to the right. All right, so the friction force, since they're both in the same direction, the friction force is doing positive work. Friction force does positive work on the book. Now we can't calculate how much work it's doing because we don't know the magnitude of the friction force. All right, and that's okay. All right, we'll work with friction in a later problem and in other problems in other videos. But basically, the applied force is not doing work. The gravitational force is not doing work. The friction force is doing work because the friction is to the right, the displacement is to the right, the force and the displacement are parallel. The friction force is doing work. Now just remember, if the question is asking, is the applied force doing work? The answer is no. Is the gravitational force doing work? The answer is no. All right, keep in mind, in a lot of problems, they will focus on the applied force and the gravitational force, which are not doing work. If they ask about the friction force, yes, the friction force is doing work. In this problem, example 3, we are allowing the book to drop half a meter straight down from rest. So we are removing the applied force of my hand that was holding the book up. All right, we're just going to allow the book to drop a half a meter straight down. Now, I don't want to quite do half a meter because I don't think I'll be able to catch it. But here we go. All right, allow it to drop straight down. Woo, okay. So the book dropped straight down a half a meter. The only force on the book was its weight, the gravitational force of the earth pulling the book down. Now remember, in the first year of physics, for the most part, we are neglecting air resistance. Air resistance is a type of friction. If the book is trying to fall down, trying to go down, the air resistance friction would be directed upwards. But we are neglecting the air resistance. No air resistance. Forget about it. All right, so the only force on the book is its own weight, the gravitational force. Now remember also, this is the definition of free fall. As long as the book is falling and the only force on it is its weight, the book is in free fall. All right, now, notice, the gravitational force is down, it's negative. The displacement is down, it's negative. Notice that they are parallel to each other. So this force is doing work. This force and this displacement are parallel. They're parallel in the same direction, so it's going to be positive work. Let's calculate the amount of work that the gravitational force does on the book. The gravitational force we've calculated a couple of times is negative 20 newtons. The displacement is negative 0.5 meters. Multiply those together. 20 times 0.5, we get 10. Negative times a negative gives you a positive. Now, the unit is a Newton meter, but a Newton meter is a joule. So, the gravitational force did 10 joules of positive work on the book as it fell half a meter straight down. In problem 4, you might recall, you are pushing on a brick wall for 10 minutes to the left with an applied force of 15 newtons. You get very, very tired, but the wall doesn't budge. Let's analyze this problem to see if work is done. So here's the hand. The hand is pushing to the left. So the applied force on the wall is to the left. F applied is negative 15 newtons. Now we really don't need the hand there because we're focused on the wall. We want to see if the wall moves. Now there are forces balancing that applied force. We'll call it a normal force, and that would be positive 15 newtons. All right, but in any case, the wall does not move. So the displacement is 0 meters. Now, right away, you know that since there is no displacement, all right, the wall is not moving, no work is done. But if we were to start trying to do a calculation, all right, now, taking this force and multiplying it by a displacement of 0, which, mind you, we don't even know what the direction is, you would find, since work is force times distance, and the force is negative 15 newtons, the displacement is 0 meters, well, anything times 0 is going to be 0. So you are doing 0 Newton meters of work, or 0 joules of work on the wall. All right, this applied force is not doing work on the wall because the wall isn't moving. In this last problem, problem number 5, we are pushing a 3 kilogram copper box to the right with an applied force of 10.8 newtons on a horizontal steel floor at a constant velocity. Now, right away, I want you to notice that it is a copper box on a steel floor. Now, you might recognize that it's very easy to look up the coefficient of friction between copper and steel. When you see words like copper and steel, you immediately think of this chart. Now, this chart is found on this website, NYS Regents.org. That's New York State Education Department Regents.org. Now, of course, these numbers apply for the whole planet. They just don't apply in New York State. Now, what you're looking up is the reference tables for physics on this website. Now, you could also just probably put this in quotes, and it'll come up in Google. All right, so approximate coefficients of friction. Now, copper on steel. For kinetic, in other words, if the box is moving, which it is, the coefficient is 0.36. If you were trying to get the box started moving, it would be 0.53. All right, so having looked up the kinetic coefficient of friction between copper and steel, we know that the coefficient is 0.36. So let's just keep that in mind as we do this problem. We'll use that number a little bit later. All right, I'm going to put it over here. The coefficient of kinetic friction for copper on steel is 0.36. All right, now, the steps. This is the last time we're going to be going over the steps for how to figure out if work is done. Step 1, draw a free body diagram. All right, now it's a copper box. I'm going to draw the box right here. Here's the box. I'll put him down a little bit further. All right, here's the box. All right, so the mass of the box is 3.00 kilograms. Now, to draw a free body diagram, okay, we don't need the surface. Here's the surface. All right, obviously the box is touching the surface, but you don't need the surface. So, I mean, you can put the surface if you want to, but we don't need the surface, so I'm going to get rid of the surface. All right, here's the box. Now, the mass of the box is 3 kilograms. To draw a free body diagram, you draw all of the forces on the box. Now, mass is not a force. We're going to convert the mass to weight. Fg equals m times g. The mass of the box is 3 kilograms. G for the Earth is 10.0 meters per second squared. So the weight of the box is 30 newtons. All right, so straight down, Fg equals, I'm going to put negative 30 newtons because it's down. Now, the box is resting on a flat surface, so the normal force opposes the weight exactly. F normal equals positive 30 newtons. All right, now I'm going to get rid of this, all right, because we got more drawing to do here. All right, now, an applied force to the right of 10.8 newtons. So here's my applied force to the right of 10.8 newtons. Fa equals positive 10.8 newtons. Now, since the box is traveling at a constant velocity, remember, we are drawing the free body diagram, all of the forces on the box. Since the box is traveling at a constant velocity, the net force in that dimension is 0. So that means that the friction, right, must be Ff equals negative 10.8 newtons. Okay, the applied force to the right, the friction to the left. Okay? And again, the reason that we know that the friction is the same magnitude as the applied force is because the box is traveling at a constant velocity. Therefore, the net force in that direction must be 0. The net force in this direction is also 0, right? Because vertically, the box is at rest. And Newton's first law says if the box is at rest or traveling at a constant velocity, the net force must be 0. All right, now, the free body diagram is done. Now, think about whether or not the box has a displacement. You push a 3 kilogram copper box, oh, gee, there it is, 2 meters to the right. Okay, so the displacement in this problem is 2 meters to the right. So just draw the displacement off to the side somewhere, right, close to the free body diagram, but never on the free body diagram. You do not draw displacement, velocity, or acceleration on the diagram. Just put it off to the side. Probably best not to put the mass on the diagram either. Just right off to the side. All right, here we go. Displacement equals positive 2 meters. Okay, so step 1, free body diagram. Step 2, is there a displacement? If there is, label the displacement. All right, now, step 3, look at each force, all right, and decide whether the force is parallel or perpendicular to the displacement. All right, so let's see. Let's do the normal force over here. The normal force is up. The displacement is to the right. All right, so the normal force is doing no work. All right, the gravitational force is down, Fg. The displacement is to the right. All right, so these are both perpendicular to the displacement. The normal force and the gravitational force are not doing work. Now, how about the applied force? All right, now I'm going to have to move this over just a little bit. Getting in the way there. All right, so the displacement is 2.00 meters. All right, now, the applied force and the friction force. Here we go. All right, F applied is to the right. The displacement is to the right. Okay, they are parallel to each other, so the applied force is doing work. They're both in the same direction. The applied force is doing positive work. So, work equals force times distance. All right, so we've got here the applied force is 10.8 newtons. All right, positive 10.8 newtons. The displacement is positive 2 meters. All right, so we've got here that the work is 21.6 joules. Positive 21.6 joules. Okay, the applied force did 21.6 joules of positive work. Now, the friction force. The friction force is to the left. You know what? I'm out of room. So let's go ahead and copy it. Pause the video, copy that if you need to. All right, I'm going to erase that because I'm running out of space here. All right. Pause it. Okay. All right, here we go. The friction force. The friction force. All right, FF is to the left. The displacement is to the right. They are parallel to each other. All right, that's parallel. All right. So the friction force is doing work. They're opposite directions, so the friction force is doing negative work. All right, now here, work equals force times distance. All right, the friction force is negative 10.8 newtons. The displacement to the right is positive 2 meters. So the work done by the friction force is negative 21.6 Newton meters, or negative 21.6 joules. Okay, now, the only last little thing I want to do, we assumed, and correctly, mind you, that the friction was 10.8. All right, let's do that calculation, all right, and just prove that. All right, so just to recap on the work, the normal force did no work because it was perpendicular to the displacement. The gravitational force did no work because it was perpendicular to the displacement. The applied force did 21.6 joules of positive work. The friction force did 21.6 joules of negative work. Now, what if you needed to calculate the friction? What if you couldn't assume that it was 10.8? What if you needed to calculate the friction? Let's do that very, very quickly. All right? All right, so we know the equation for friction, FF equals mu F normal. Now, mu, for copper on steel, it's moving, it's kinetic, is 0.36. Mu, the coefficient of friction, does not have a unit. The normal force is 30. The normal force is positive 30 newtons. All right, so get out your calculators. What's 30 times 0.36? All right, what's 30 times 0.36? Put it in your calculator. What are we getting? We're getting positive 10.8 newtons. All right, now we know the direction is that way, so we simply say, okay, it has to be negative. All right, so again, if you needed to calculate the friction, you could do that. You just have to look up the coefficient of friction between copper and steel. All right. In this, actually the last two videos, all right, this video and the video just before, 6.01 and 6.02, we figured out more or less, well, we did qualitatively first. We talked about it a lot in the first video. The second video, we did a lot of quantitative work. We got all the numbers. Now, what are some of the steps to figure this out? Number one, draw a free body diagram. All the forces on the object that you're talking about, the object that is either moving or not moving. Number two, determine if there is a displacement. If there is no displacement, no work is done. Right? If there is a displacement, then write down the displacement. Here we did, right there, right off to the side, not on the free body diagram. Number three, look at each force. Forces that are perpendicular to the displacement are not doing work. All right, forces that are parallel to the displacement are doing work. All right, number four, the equation for work equals force times displacement. Now the force has to be the force that is parallel to the displacement. Finally, in this case, also, since the net force in this direction is 0, all right? Positive 10.8 plus negative 10.8. since the net force is 0, the net work is also 0. The work that this applied force did exactly cancels the work that this applied force did. Okay, work is done by both forces, but the net result, the net work, is still 0 joules. Right, again, let me just repeat that. Work was done by this force, work was done by this force, but they opposed each other, so the net work is 0.